Good day, everyone. Thank you for joining us for another webinar from Adaptiiv. And today we have the pleasure of featuring a special guest from St. Luke's Radiation Oncology Network in Dublin, Ireland. And our guest today is Ciaran Malone, medical physicist there. Ciaran and St. Luke's have been a customer of ours for almost 2 years now. And Ciaran's going to take us through his and his network's experiences with implementing, commissioning a 3D printing solution as they use it in radiation oncology. So he'll take us through, how they kind of got set up with 3D printing, how they're using it, and how they're using the Adaptiiv software to treat patients and some clinical examples. So really excited to have him here. I'm just going to get through one intro slide on Adaptiiv, just for those that don't know anything about our software or very little about our software. I'll give you a little overview, and then we'll get into Ciaran's presentation. For those that do know, we are an advanced software solution that is used to create 3D printed accessories that are used in radiation therapy. So we have 3 modules in our software, which you see on the top right here on this slide. One's called uniform thickness bolus or simple bolus, another for modulated electron bolus, and one for HDR, high dose rate surface brachytherapy. So there's photon and electron treatments that our software is capable of designing accessories for. We use patient CT scan data within our software and those CT scans to create and design these patient-specific accessories that are then 3D printed with a 3D printer of your choosing. We have one that we validated, which I'll get to in a second here, and are currently validating more printers. So definitely not limited by any printer, but we have done some legwork on validating a printer with our solution, which is nice. On our solution, we are fully regulated, so feel that and it does separate us and set us apart from some open source or free softwares out there that aren't regulated by bodies you see here, like the FDA in the US. We have our CE mark in Europe, approvals in Australia as well as New Zealand, and our ISO certification. We have a QMS that's backed, quality management system that's backed by ISO certification. So very, we feel it's very advantageous. We do have integration, as you see here in the last bullet, with clinically commissioned TPS with most major TPSs. So you're able to export the design from our software, which again is based on patient data, back into the TPS for verification and dose and plan verification. So you know what your treatment plan is what you're going to deliver. And on the printer, we've spent more than 5,000 hours, printer and filament materials. We're approaching 6,000 hours almost on validating. The printer you see here on the bottom right is the Axiom 20 made by Airwolf out of California. But in the upcoming weeks, we actually are going to release some new printers that we've been working on validating. So yeah, without further ado, I'll let Ciaran give a full introduction on who he is. I won't do him any injustice or I'll sell him short here. So what I'm going to do is allow Ciaran to take the screen here and drive the bus, and then he will take you through his work and his findings.
Hi everyone, and thank you, Rod, for allowing me to come along and share our experience in using 3D printed technology in our network. So as Rod said, I'm a medical physicist in the St. Luke's Radiation Oncology Network in Dublin. And just as a quick disclosure, I have been given the opportunity to share some of our work here in SLRON from Adaptiiv. So just an overview. What I'd like to do is start on the how and why we implemented 3D printing in our network, and then move on to a little bit of the commissioning that we did, our experience using 3D printed bolus clinically, how we've begun work on MART and surface molds using 3D printing, and just some of the other things you can do when a 3D printer is in your department regarding research and development. So in our network, it's comprised of 3 different centres. So the St. Luke's Hospital, St. James's Centre and Beaumont, located in Dublin, Ireland. And we have radiotherapy, brachytherapy, nuclear medicine, and across all the 3 sites, we have 6 CT simulators, 14 inner accelerators, and treat approximately 5,000 radiotherapy patients per year, of which we'd expect maybe 200 bolus cases. We have a very strong mold room in our most southern site, and really when the adaptive solution came into our minds, we really wanted to see, could we put complex and customized bolus solutions in our other sites to complement the work that we have, our mold room in our small southern site. So the solution we went with was adaptive, as I said, and really one of the biggest reasons we went with it was that we don't need to create any bespoke software ourselves. We don't need to kind of learn or try to choose a 3D printer that would fit into exactly, that would meet our needs. So it integrates directly with our radiotherapy workflow, and we have those 3 modules that Rohit introduced, which is a simple bolus, modulated electron radiotherapy bolus, brachytherapy surface molds, and as well as that, you have a printer in your department. You can use it for any idea that comes along. So 3D printing, for people who may not be 100% familiar with it, it's the solution that we have is a fused deposition modeling type of printer. It's a nozzle diameter of 0.5 to 0.8 millimeters. So this means it really meets any needs for the complexity or precision you need for a bolus, or for a modulated bolus, or for creating those really narrow catheter trajectory lines for a surface mold. Prints are built up layer by layer until a full 3D model is complete. It can be almost any shape or geometry, so really what you can design your treatment planning system is absolutely no problem for a 3D printer to achieve. The printer that we have is an Axiom 20, so we have quite a big print area. So we printed things like full leg wraps, so any of the prints that we needed clinically would fit in this large print area. Materials, we've had the opportunity to use several different types of materials, of which would be very flexible materials like NinjaFlex or Wolfbend, very rigid materials like ABS, and a newer material called CheetahFlex, which just allows you to print that little bit faster, because for flexible type materials, you do need to reduce your print speed. So it was great to be able to try out a filament which has both speed and flexible benefits. And this is where we lie. So the 2 materials we lie in terms of density are, close to water equivalents, so ABS and TPU. But what really excites me from a physicist point of view is the range of materials that you can print with. So if you have an idea for something that might require something of a little bit higher density, there are loads of filaments available. And I'm sure if anyone does get a 3D printer into their department, you'll have hundreds of ideas coming down the line, and each and every one would have a filament that would suit that particular use. So the workflow that we have is, initially we export our CT data and structure set to 3D bolus. So we would have designed something in a treatment planning system using the contouring tools available. Any structure that we have in a treatment planning system can be converted to an STL file. So we have Monaco, OMP, and Eclipse in our network, and we've used 3D bolus for all 3. We can add patient identifiers using the 3D bolus software. You have a crop plane to make sure that there's a flat edge for printing. You can cleave the bolus in 2, and now this is a feature that's actually quite useful, because if you wanted something that would wrap around a leg or an extremity, you can cleave it into 2 or more parts, just to try and ensure that for setup for the radiation therapist on the treatment units, that it's quite quick and efficient and easy to set up with minimal impact to the patient. You can have TLD dissymmetry. Now, as of yet, that's untested by us. We've actually used it for putting little setup marks for projects and that, but so far we've not actually used that clinically yet. And the last thing, then you can export your model to a 3D printer for printing. We've actually implemented a care path in our system, because since we operate over a network, anybody in the network can say, I would like to create a 3D printed bolus, for example. And in that case, a treatment planner would drop this care path into ARIA. And once they've completed their particular design or bolus that they have in the treatment planning system, they can tick their task off, and it becomes available for physics and engineering. And what we do then is we check the print, that it is suitable to print, and maybe make sure that we have enough resources to print that particular print. Maybe it might take a little bit longer or shorter, it might need a little bit more support. And we send it to the printer, QA it, and then once those tasks are complete, it's sent straight to the treatment unit. So it just allows everyone in the path to know where that print is at any particular time. So commissioning the 3D printer, what we did was we used multiple slabs of 10 by 10 centimeters of varying thicknesses, so 2, 5, and 10 millimeters thick. We also printed a CT electron density insert for our Sears Phantom. And the first things we wanted to do was evaluate the printer settings that we would use. So we really wanted to have a material specific profile for each printer material we'd use clinically. And the reasoning for this is that anyone could come along, they could load up the printer profile and click print, and they could then, when they return, they'd be sure that the print would be ready for them and waiting once complete. The other question we wanted to look at was the geometrical accuracy and reproducibility. So the max difference that we found in the XY direction was 0.9 millimeters, and in the depth dimension it was 0.3 millimeters. So this is the type of precision that we were very happy with, because if you're manually making bolus materials or molding thermoplastic beads, you know, that type of accuracy or precision is not really achievable. The next question we looked at was the homogeneity. So here you can see on the right is one of our Sears electron density inserts for wolf bend in this case, and the max variation that we found was about 10 HU across that particular print. And we found very similar type of homogeneity for Ninja Flex as well. So we were very satisfied that these prints were coming out homogeneous and wouldn't cause any dosimetric issues. And the last type of question we wanted to answer was what HU represents the material's electron density. And to do that, we followed a paper called Burleson et al. And what they did was they measured TMR or PDD type measurements, and they adjusted the density that they had in their treatment planning system to match measurement to calculated. And then once they had an appropriate match, they used that value for all future TPS type calculations. So for us, for wolf bend, we found plus 100 HU represent the material's density, and minus 50 HU for Ninja Flex. So very close to water equivalence. One paper that came out after we did all of this work was really reassuring actually, which is Material Matters, an analysis of density uncertainty in 3D printing and its consequences for radiation oncology. And really what they were looking at was they printed multiple different cubes. They want to look at the variance in density for printed objects, if that density varied over time, and the clinical dose uncertainty caused by variations in the density of these objects. So because we followed a lot of the guidance of this paper actually concluded that we were quite reassured that we followed the right path, basically. So they found that of each 10 printed blocks, density was tracked over 5 weeks with minimal changes, very little variation between each one of the blocks that was printed. And the density differences resulted in differences in the position of the 90% isodose line for up to 9 millimeters for assuming water equivalence, assuming if CT density is correct, up to 3 millimeters. And lastly, the average measured density, so actually going and specifically measuring the density of that material, was up to 1 to 2 millimeters. So that last point is the one that we followed using the methodology by Burleson et al. And we were quite satisfied then that we were at least along the lines of what others were doing too. So to move on to our clinical experience using 3D printed bolus, I mean, we've printed boluses for nearly every anatomical site at this point from head to toe. So I'll share a little bit of experience with that. And I mean, I should really start about like why we need bolus. I mean, for those who may not be too familiar with it or might be coming from a different area or looking at it from maybe a brachytherapy or some other area, I mean, we need bolus because it removes this skin sparing effect that we have for megavoltage photons and ensures the skin receives full dose. However, for difficult sites to bolus, you might have air gaps and gaps between the bolus and the skin surface, which would degrade this bolusing effect. So what we were really interested in was to see for these difficult sites, could we achieve better conformity and minimize air gaps using 3D printing and really see would 3D printing really help us in this area? And looking back on different cases and in the literature, and you can really see that bolus is not perfect in all circumstances. You can have consistency issues, conformity issues, and patient comfort is paramount as well. So the 3 areas we really wanted to see was, could we find different clinical sites that would benefit from a 3D printed approach that would be consistent and very conformal and ensure that patient comfort is maintained. So using an audit type approach, we looked at all the 3D printed bolus, all the 3D printed sites or boluses we generated, and we had just over 60 or so in this particular audit. And you can see that the head and neck was our most common site that we had a request for a 3D printed bolus for SCCs and lymphomas typically. So to just go into some of those head and neck cases, I mean, this particular one was an extensive BCC involving bone. We tried multiple different types of boluses like superflap and customized thermoplastic bolus. And as you can see at the top image, we had to go down to a 5mm bolus because it was just very uncomfortable for this patient. And I mean, the weight wasn't evenly distributed over the patient's surface. And it was, I mean, the patient's, you know, the patient comfort was such an issue that there was a query over would this patient even tolerate continuing treatment. So we decided to print the original planned bolus and with our most flexible material and try it on the patients for the next fraction. And it was much better tolerated. It really evenly distributed that weight across the entire surface, which is great. And the treatment was able to proceed, which was very, very positive. Another case that I wanted to bring up was a lymphoma, where the radiation oncologist requested 1 centimeter thick bolus over the brain region and 5mm just over the eyes and face. And I mean, this is something that would be very difficult to achieve. Well, it wouldn't be very difficult, but it would be more difficult to achieve using maybe you know, traditional bolusing methods and where you'd match the two or how you'd mold it to that particular thickness. So contouring was done by the planners using Eclipse contouring tools. It was sent straight to the 3D bolus software package and sent to the printer. And you can see in the bottom image, it fit quite well, it matched the planned bolus extremely well, and there was no issues on set at all. So we were quite impressed with what we could achieve with a 3D printed approach. Another area that really came about once we started implementing a 3D printed type bolus for head and neck cases was when all these areas underneath the immobilization mask, or at least between the immobilization mask and the headrest, for our setup, if we wanted to bolus in that region, it would typically be trying to stick pieces of bolus in, put the immobilization on, and just hope that it would stay in place. So really what we found here for this particular case is we'd have to go back in, take the immobilization mask off, reset up this patient with the bolus in place, and then continue. So we were curious to see, could we fill this cavity with 3D printed bolus? And it was planned in our treatment planning system, and would it be better than what we already had? We found that it worked extremely well. So we could contour that area, it would be part of what would be planned, so the planning system would take it into account. It fits perfectly in that cavity, so in one way it's very easy to set up because it fits in one place and one place only. And the radiation therapists were very, very happy with this approach. So we were quite, this has now been a case that's been requested multiple times. And really, just to summarize head and neck overall, I mean, it was our most successful site. You can see you can avoid the eye region, you can bolus over the nose quite well, and you can make nose blocks and different other things. So really, whatever we needed for the head and neck region, it was quite a successful region for a 3D printed bolus approach. The other region that worked quite well for us was extremities. So this case was a recurrent T-cell lymphoma. It's very difficult to bolus extremities because it's a very curved surface. When you're trying to fit flat sheets over a curve, there's going to be air gaps somewhere. And in this case, it was the entire foot and ankle that we wanted to bolus. And treatment setup times for these cases are usually quite long, laborious, and in some cases do result in an inconsistent coverage over the entire region. So in this case, we printed something that would go over the entire foot and ankle and over the immobilization mask. And we made a slit down the sole. So just in case we needed to account for any edema or swelling, we could use tape, leukoplast tape, wrap it around the foot and just close that open so it's nice and snug. The bolus conformed extremely well and was very easy to set up day to day. So it was quite a time-saving effect in terms of what we used to do compared to what we did with the 3D printer. This was another case where it was actually a full leg wrap. And in this case, we wanted to bolus the entire leg and cover multiple different sites of disease. So what we did was we printed that entire leg, and we again made a slit down the side such that it could be opened and closed around the leg, and closed with tape as well, just to make sure that the fit was nice and snug. And in this particular case, what we used to do was actually wrap the leg in lots of different bolus, or lots of different sheets of bolus, and it would be quite long and laborious to do so. And for this particular case, we were quite impressed with just the time saving that we were able to achieve, and it was a lot more comfortable for the patient in the sense of the setup times were reduced. So the learning to date, we really had quite a learning curve in terms of which cases would benefit and which cases didn't quite benefit from a 3D printed bolus approach. So for us, I mean, if standard bolus works, go down that line by all means. But for us, head, neck, and extremity cases were definitely the sites that had the biggest advantage. For sites that had very mobile tissue, say for, in some cases the larger breasts, you know, with 3D printed bolus, unless you print with an extremely flexible material, you know, you may encounter difficulties. So for us, minimal contour change is expected, and if the tissue wasn't mobile, so for us, head, neck, and extremities were the two sites that we really had very positive impacts to our treatments. For planning, I mean, you really need a good definition of your body mask, your body or your mask contour, because the printer will print precisely what you give it, which is great on one side of things, but you just have to make sure that you're defining that body contour as accurately as possible at the time of treatment planning. Cleaving the bolus now is an incredibly useful feature. It came about as we were using this package clinically, and that's one of the advantages of working with the Adaptiiv team was that, I mean, some of that feedback that we would have given them was actually implemented quite quickly, and I mean, that cleaving feature is absolutely fantastic, and treating RT feedback is invaluable. So, I mean, from an MTT approach, a 3D printed solution can really fit snugly into your clinic. For the printer itself, I mean, for complex boluses, you really have to think about the support requirements, because you can't print over nothing as the print progresses. So you need to consider what sides of this print will the supports be printed on, in which case then when you peel them off, it is a little bit of a rough edge, but we always make sure that the surface of the print not in contact with the patient is printed with support such that the side that contacts the patient is nice and smooth and snug. We did a bit of an audit again with, after printing all these different prints, we brought them all back and assessed, you know, how the density did vary over all these different prints. And we found that for Wolf Bend, we initially found 100 HU was our initial commissioning value, and then we brought all these different prints back, so different sizes and shapes and thicknesses. We found that the mean was about 75 HU plus or minus 22 HU. So clinically, we were quite satisfied that it was doing what we wanted it to do. We found as well that we could splice filaments together. So if you wanted to leave the printer over the weekend, I mean, you're not really stuck if you're still printing with the end of a roll or a spool. You can splice loads of them together and keep that print going. And finally, for the printer side of things, we have found, say, a nozzle replacement and a full in-house type service every year would be required from our side of things, from our experience. And nozzles are quite handy to change, so you just screw them off and screw them on again, and you're ready to go again. So I'd like to then move on to the other packages, because we did a little bit of work with both. So the first one was the modulated electron bolus, which one of our resident medical physicists, Majid, has done quite a lot of work on, and hopefully they share some of it today. Now, he's actually hoping to publish quite soon, so only some of the results I can really present at the moment. So hopefully, if that's successful, you'll see the full set of results in the near future. So for modulated electron radiotherapy, you really want to preferentially attenuate your electron beam in regions where you want to pull up that 90% dose distribution, such that it would give you a lovely conformal dose distribution around your target and spare any underlying structures. How it does that is just by increasing or decreasing the bolus thickness that is used. So for example, here you can see a case on the very top, A, where you might want to spare maybe the eyes and treat the nose. And B is a kind of a wedged type distribution, and C might be something like a scalp or something that you'd want to treat in a very conformal way. So the first thing that we wanted to look at was to see, well, what is the process and what can be achieved under simple circumstances. We took those kind of simple shapes and features, and just to see, you know, in this case, 2 iterations were required, which is you use one iteration first, it gets the conformity right, but because electrons scatter so much, you may have a very high Dmax. Your second iteration through the 3D bolus software then would ensure that those hotspots are taken care of. So in this case, we ended up with a Dmax of 103% and quite a nice conformal dose distribution compared to what we would have, say, started with. You do have to, what we've typically found is you kind of over-cover a little bit, and it gives you lots of options to, and it gives you a lovely conformal dose distribution in the end. Overall, we found that yes, with a bit of an increase in Tmax, you maintain a good coverage, but the biggest sparing was this normal tissue receiving 90%. So we found that in approximately 30% of your normal tissue has been spared using a modulated electron radiotherapy approach. And we have found that you can actually tune this, and this was a feature that, because of a bit of the feedback from a number of sites with Adaptiiv, they said this might be an interesting feature to add, is actually to tune that hotspot correction a little bit. So you can go from a completely uncorrected bolus, which is to say one iteration through, and we had quite a high Dmax, which is probably not acceptable in this case, but very, very conformal dose distribution. But as you tune this hotspot correction down to say 20% or even off, you can then say, well, we're going to compromise conformity a little bit to get our Dmax in, or we'll allow the Dmax in our plan to go a little bit higher than usual, just to get that conformity we need and that sparing of underlying structures. So it's quite neat to be able to do that in the software. We did quite a bit of validation, and this is a lot of the validation work now. I hope if we get this publication through, you'll see in the near future, but I'll share some of the preliminary results. So initially we looked at 4 different simple PTV shapes: a step, a wedge, a groove, and a triangle, and we used EBT3 film in both parallel and perpendicular geometries just to validate what we had planned is what we're actually getting. And we found very, very good results. So for 3% 2 millimeters for this kind of step, or this step type bolus, we found 97.6%. A pass rate in perpendicular to the beam, we found about 96.8% as well. And you can see with the ISO's contours, it's a little bit noisy with the film, but it was quite a good agreement. Again, for a different type of distribution, so you can see here for this more complicated type distribution, we also had very, very good agreement as well. For surface brachytherapy applicators, one of our other residents is now a physicist in a different center, but she did some great work in terms of looking at the surface molds. So the idea or the concept would be to move away from the kind of manually created maybe wax surface molds or the free brick flaps, and see could you get something very precisely printed, because this is where a 3D printer really excels, is precise prints that could maybe give you that precision and accuracy you need for, say, a surface mold, because that real steep dose drop off, I mean, that would be where your advantage would come from. So she actually got this work published in Physica Medica quite recently, and some of the work really focused on the material itself. I mean, could we classify this material as water equivalent? And secondly, you know, we're going to verify some geometries and using measurement to see is the dose that we expect correct. So in this case, she printed a very curved phantom and used EBT3 film. You can design how many trajectories you want, the distance each trajectory is away from the surface, and the tunnel radius itself. So you can match your system precisely. As well as that, you can tune each trajectory. So you can say then, oh, I'd like it a little bit closer here, a little bit further away. And then you can reconstruct those trajectories yourself in your planning system. And what we found is a very good agreement between bolus and water. So we substituted the printed mold itself with a single trajectory through, and with both parallel and perpendicular to source travel arrangements, and we found a very good agreement with water. In different geometries, so say here we can see in film measurements, you see again a very, very good agreement for both parallel and perpendicular to source travel. And just to finish up with other 3D printed applications, so I mean, having the 3 packages there are brilliant, and we can also use them then for any sort of research and development work you have in your department as well. And this is where we really found an advantage of a 3D printer in the department came to light. Our first example would be a pediatric headrest. So we initially had all these adult headrests, and you know, they're not maybe ideal for the pediatric cohort that might come through for TBIs. So we decided, could we just design a really soft, spongy type air equivalent headrest that would be customized for the variety of different pediatric patient sizes that we'd see. So we printed a 10% fill, and it was very spongy, which is great, and it was very close to air equivalence. And we found that it worked extremely well for our pediatric TBI cases. So now what we hope to do is print a number of more a larger variety, such that we could pick the one that's the best fit. Another example would be printing phantoms for different validation or other research studies. Here we just printed a pelvic phantom that you could have inserts with different volumes or different sizes, or that could answer different questions. So having a 3D printer really allowed you to print the exact tool you need to answer your question, which is really, really good. And we've had several different projects come through, everything from headrests to phantoms to even a little LINAC to help in training for treatment planners. So really, I mean, the message here is, I think if you have an idea and you have a 3D printer, you can make it. So thank you very much, everyone, for listening. If there's any questions or comments, so I just want to make a special thank you to all the people that contributed to the work in our network regarding the 3D printer, and making it a very, very big part of our network in terms of making customized boluses and equipment. So thank you, everyone.
Thank you so much, Ciaran. That was a great overview of the experience that St. Luke's went through in commissioning and implementing 3D printing solution. That was really great. Thank you so much. Now, there have been some questions coming in from our audience today, so we'll get to that right now. How about that? So, Ciaran, first question. Actually, I'm going to, I'll let you still drive the bus here. So, in terms of implementing a 3D printing solution, the printer and software together, what would you recommend to a center looking to do that? What are some of the best practices you could maybe pass along?
I think from where we started to now, I think there's quite a lot of work that's been done that you can refer to. For example, that Burleson et al. And the paper that looked at the different effects of uncertainties in 3D printing. So I think the very start would be, where would you use the printer, or what would you use the printer for? We started off using it for just simple bolus type applications, and through doing that, I think we learned a lot, because it's an area we're very familiar with. We know about bolus, we can assess it on set, and we know what's right and what's wrong. And so it really gave us a feel for what the printer could achieve and how we could use the printer to the best of its capabilities. And we learned a lot from doing that. So I think anyone that would want to implement a 3D printer, look to the literature, see what everyone else is doing. I would recommend having very consistent print profiles, and have a validation of each material that you want to use, but use it for something simple first, such that you can really get a feel for what the printer can do, and what the printer might be. You might need to build your experience when you need to move to the more complicated things like maybe surface molds or MERT.
Yeah, great answer there. And we actually at Adaptiiv have some validation documents that we've prepared, similar to how your team did it, Ciaran. So we can pass those along to anyone who is interested and would like to know more. Just let us know. Okay, next question. As you and the center and the network were building out, I guess, the business case to invest in a 3D printing solution, our software along with that, what would you, I guess, recommend to another center looking to build a case to adopt something like this? I mean, I guess you mentioned time saving was a big benefit that you achieved, and definitely, geometrical accuracy and things like that. So maybe you could elaborate a little bit on how you built the case and what, I guess, your argument was to implement a 3D printing solution.
Yeah, I mean, time is quite hard to quantify, but in certain cases, like for those extremities, I mean, it was quite clear that if we could print one single bolus that could be placed on set, or at least one that could be cleaved in two and placed, it'd be quite advantageous. But initially, what we looked at was what bolus materials we use currently and what they're costing us to use, to see then if we were to, say, print the same bolus out of a 3D printed material, what the equivalent cost would be, and would there be a cost saving. And what we found was, for a lot of the complicated cases where we were cutting sheets of, say, superflab, or using very specific bolus types, there would be a cost saving in terms of using a 3D printer, which, I mean, materials for 3D printers I mean, they're not expensive relative to a lot of the other things we use in, say, radiotherapy in hospitals. So there was a cost saving argument to be made for us. The next case would be the time saving aspect of it. So yeah, we had to, use a bit of guesswork to say, well, for those extremity cases, it actually took a considerable amount of time to bolus both at CT, but then at every single fraction after that. So for us to have something that could be cleaved in two, like I said, would be very, very advantageous. And the third thing would be, you know, in terms of just the advantage of having something on site that we didn't need to go to, say, our mold room in our most southern sites. So we're based in the three centers, like I mentioned. So if we wanted a very customized or specific thing made, it might take a little bit longer. And then the whole advantage of having something on site that you could go and sit face to face with somebody and work through any issues or any sort of complications to come up with the best solution for a particular patient. I mean, it was great to have. So we just made the argument over those three kind of areas of, you know, something that would be local, something that would save us in terms of time, and something that would be a cost saving for those really complicated cases. And that's what we tried to focus on when we initially implemented it as well. So for simple bolus type cases that we typically struggle with, that's what we tried to start with.
Yeah, no, great insight there. Thank you for passing that along. I think the in-house or the on-site advantage is very important that we hear echoed by a lot of our other customers as well. It being able to integrate with the TPS too and verify and validate your plan is also important that we've heard. And you mentioned it, Ciaran, throughout your presentation, but the comfort, patient comfort, improved comfort with some of the you know, the materials that are being printed, and the overall patient experience is something we've heard as well. So it sounds like that, yeah, would be the same. Yeah.
Definitely the integration is actually quite an advantage, because I mean, we could try going down the line, say, of making something very bespoke, or, you know, buying a 3D printer that we wouldn't have been very familiar with, but it was great to have that package, that what we'd focus on then is how we're going to use it, rather than how are we going to set it up, and what will we possibly do, and how will it actually link in, and will it work for all the different cases. So it was very reassuring to know that it was a workflow that would integrate directly with our treatment planning system, certainly.
Yeah, that's great. Thanks again for adding that insight. Yeah, great to hear. So I think in the essence of time, and I know everyone's busy, we'll wrap up today. There's some additional questions that have come through. So what we'll do is we're going to follow up and send a recording of this webinar out to everyone that was in attendance today and that is registered, and we'll add the answers to those questions that we didn't get a chance to answer today within that email. I would really like to thank Ciaran and his team at St. Luke's for all that they've allowed us to present on our behalf. I know I met Ciaran earlier in the middle of 2019 in June. We had an event with Ciaran and his team in Dublin, and so the people you see on this slide, I met a lot of them, and it's an amazing team that you have there, Ciaran, at St. Luke's, and you're doing some really innovative, forward-thinking and breakthrough type of applications of 3D printing in terms of treating cancer. So kudos to you and your team and all the great work you're doing and continuing to do. And yeah, definitely pass along a big thanks to the Friends of St. Luke's as well for their support in allowing the Radiation Oncology Network there to be able to use our solution in 3D printing. So unless you had anything else to add, Ciaran, any parting wisdom or thoughts you'd like to share?
No, that's it. I mean, if there's any further questions, I'm sure we can follow up with some answers. So yeah.
Absolutely. Okay, thank you again very much to yourself, sir, and thanks to everyone for joining us today, and we'll be talking to you soon. Have a great one.